Today we will be graphing rational functions and analyzing the graph. If we look at the function f of x equals 1 over x plus 2, what do we notice about the equation itself? Meaning, what do we notice about this guy for itself? Well, one thing that jumps out at me that is when x equals -2, I know that's what x cannot be, for sure, right? Because it gives me 0 in the bottom of the fraction. So notice how in the picture, we don't have an x value that is -2. How do we find the y-intercept? Well, we would replace the x's with 0, 1 over 0 plus 2. So we should have a point on our graph at 0, 1/2. And for x-intercept, remember you replace the y and make it a 0. So if we were to replace the y and make it 0, we have 1 over x plus 2. When you multiply both sides by x plus 2, we have 0 equals 1, which does not exist. So that means we don't have any x-intercepts. So notice in this graph, there are no x-intercepts. If we go to the middle picture, notice the graph looks different. Well, what do we notice happens in the function g of x? Looks like the x plus 2's are going to cancel out, and all we have is y equals 3. But remember, our domain, x cannot be -2. So this open dot in our graph is what we call a hole. So we would take our reduced form and replace the x value with -2, which in this case there isn't one. It's just 3. If we look at the third picture, notice we have 2 places where x is undefined. We have x cannot be -2, and we have x cannot be 1. And notice that we have an open dot, again a hole at -2, and at 1, notice we have no x values here. Okay, because these are like, they cancel out. So our numerator becomes a 1, the denominator is x minus 1. So just something to start thinking about. A rational function. Oh my god. A rational function is a function in the form f of x equals p of x over q of x, where p of x and q of x are polynomial functions. The domain f of x is real numbers except for those values in which q of x equals 0. Okay, so just like we talked about with our previous graphs, if I have 0 in any place in the denominator, it is a restriction. So we have a few different types of graphs we can look at. Notice we have f of x equals x squared plus 1. Notice I don't have any place where x is undefined because x squared plus 1 is I when you solve plus or minus I, which we don't graph. We might have something like the g of x function in which the x plus 2's reduce down, and it looks kind of like the picture we looked at before. And we could have something like h of x, where we can't have x be 2, and a continuous graph is a graph that has no jumps, breaks, or holes. In other words, you draw the graph and your pencil never leaves the paper. A discontinuous graph is a graph that has a jump, a break, or a hole. So in our examples, the first one is continuous. The middle one is discontinuous because it has a hole. And the third one is also discontinuous because it has a break. A point of discontinuity. Okay, so if a is a real number for which the denominator of a rational function f of x is 0, then a is not in the domain of f of x. The graph of f of x is not continuous at x equals a, and the asymptote has a point of discontinuity at x equals a. So the graph of g of x equals x plus 2, x plus 3 all over x plus 2 has a removable discontinuity at x equals negative 2. This is because I can reduce the fraction down, so we call that a removable discontinuity. The hole in the graph is called this because you can make the function continuous by redefining it at x equals negative 2, so that f of negative 2 equals 1. Okay, so what that means is if you plug negative 2 into the reduced form, you do get negative 2 plus 3, which is 1. A non-removable discontinuity would be something like h of x, in which nothing cancels out the fraction, like the fraction is already reduced. So we have a non-removable discontinuity at x equals 2 because there is no way to redefine the function at 2 to make the function continuous. So in our next few problems, you're going to have to do this on the formative. Get excited. We're going to be given a function, and then we're going to answer the following statements. If it were me, I would put it in factored form as much as I possibly can. So I know the numerator is going to stay x plus 3, but the denominator, I'm going to have to factor it. If we have factors of 3 that add to give us negative 4, that's x minus 1, x minus 3. Notice nothing cancels out. Now we're ready to answer our questions. So our domain. Where x is undefined, we know x is undefined at 1 and 3 if you set x minus 1 equal to 0 and x minus 3 equal to 0. So our smallest x value is 1. So our domain is negative infinity to 1 with parentheses, union from 1 to 3, union 3 to infinity. Okay, so this represents all x values except for 1 and 3. A non-removable discontinuity is the denominator of the fraction where it doesn't reduce down. So in this case, x equals 1 and x equals 3 is our non-removable discontinuity. A removable discontinuity would be as something were to cancel out of each, the numerator and denominator. In this case, we don't have anything. Okay. If we move over to D for holes, we only have a hole if we have a removable discontinuity, so we don't have a hole. Remember, for x-intercepts, you are thinking to yourself, y equals 0. So if you plug in our g of x example, x minus 5 divided by x squared plus 1, our domain this time is going to be all real numbers. And the reason why it is all real numbers is because we have no restriction in the denominator. If you set x squared plus 1 equal to 0, you do get x squared equals -1 and x equals plus minus I, which in this case doesn't really make a difference. The non-removable discontinuity, then, we don't have anything. None. For removable discontinuity, notice the fraction is already reduced to lowest terms, so we don't have a removable discontinuity. If we don't have removable discontinuity, then we do not have a whole. Our x-intercepts, remember you're going to replace the y and make it equal to 0. So if I do 0 equals x minus 5 over x squared plus 1 and multiply both sides by x squared plus 1, we get 0 equals x minus 5. Remember, for x-intercept, I'm thinking in my brain, set numerator equal to 0. So if I set x minus 5 equal to 0, we get x equals 5, or the ordered pair 5 comma 0. And then for y-intercept, remember, you will replace all the x's with zeros. So for y-intercept, we'll have 0 minus 5 divided by 0 squared plus 1, or 0 negative 5 for our ordered pair. Ta-da!
Example you try.
In our next example, again, I would probably put it in factored form if I can. The numerator will factor to x minus 4, x plus 1. Now, notice what happens this time. The x minus 4s are going to reduce, and we're just left with x plus 1. For our domain, remember, we still have to state, look at the original problem. So we still cannot have x be 4. So our domain, negative infinity to 4, union 4 to infinity. Non-removable discontinuity, this time we don't have one because in our reduced form, we don't have a denominator. However, we do have a removable discontinuity because x minus 4 is canceled out. Our removable discontinuity is that x equals 4. To find our whole, I'm going to replace the x value and put it into our reduced form. So 4 plus 1 is 5. Therefore, our whole is at 4 comma 5. X-intercepts, remember, for x-intercepts, we're going to set the numerator equal to 0. If I set x plus 1 equal to 0, we do have an x-intercept of -1, 0. For the y-intercept, remember, I replace all the x's in the original problem. So 0 squared minus 3 times 0 with a 0, and then simplify. Notice that we're really only going to look at these because everything else is 0. So it's like we set the constants, we divided them into each other. Our y-intercept is 0, 1. Vertical asymptotes. Okay, so the graph of a rational function, f of x equals p of x over q of x, has a vertical asymptote at each real 0 of q of x if p of x and q of x have no common factors. Okay, so we have a vertical asymptote each place in the denominator of the factored form. If p of x and q of x have x minus a to the mth power and x minus a to the nth power as factors, and m is less than n, then f of x also has a vertical asymptote at x equals a. So we're going to factor the denominator. Let's go. So our numerator is x plus 1. Denominator is x minus 2, x minus 3. So the first thing I would do is I would see if anything needs to be factored. And then the vertical asymptote, you just set each piece in the denominator equal to 0. So x minus 2 equals 0, and x minus 3 equals 0. So our vertical asymptote is x equals 2 and x equals 3. It's very important you have the x. In letter B, remember you're going to want to factor the denominator. The numerator is unfactorable. We leave it as x minus 2. Denominator, this time, factors of -6 that add to give us positive 1 will be x plus 3 and x minus 2. Notice this time our x minus 2's are gone. So we're left with 1 over x plus 3. Now we just set that denominator equal to 0, and we get a vertical asymptote of x equals -3. Take a minute or two and try the example you tried. Hopefully you found the vertical asymptote for letter A to be x equals 1 and x equals -3. In letter B, because the denominator reduces out, we do not have a vertical asymptote. A horizontal asymptote of a rational function. To find the horizontal asymptote of the graph of a rational function, we're going to compare the degree of the numerator to the degree of the denominator. Oops, I should use a highlighter. Compare the degree of the numerator with the degree to the denominator. If the degree of the numerator is less than the denominator, then we have, x-axis is our horizontal asymptote, or y equals 0. If m equals n, the graph has a horizontal asymptote at y equals a over b, where a is the coefficient of the term of the greatest degree in the numerator, and b is the coefficient of the term of greatest degree in the denominator. If the degree of the numerator is larger than the degree of the denominator, then we do not have a horizontal asymptote. So if we look at our next example, we're going to find the horizontal asymptote of each function. So if we look at letter A, the degree of the numerator, notice, is linear, and the degree of the denominator is also linear. Because the exponent of the numerator equals the exponent of the denominator, we divide the leading coefficients. So our horizontal asymptote is the equation y equals 2 divided by 1, or y equals 2. For letter B, notice the degree of the numerator is a 1, whereas the degree of the denominator is a 2. So our horizontal asymptote is going to be y equals 0 because the degree of the numerator is less than that of the denominator. In letter C, notice that the degree of the numerator is 2, whereas the degree of the denominator is 1. Because the degree of the numerator is larger than the degree of the denominator, we have no horizontal asymptote. Take a minute or two and try finding the horizontal asymptotes of the U-tray. Hopefully you found the horizontal asymptote is y equals 0 for A, for B, no horizontal asymptote, and for C, y equals -2. Intercepts. Last but not least, graphing. When we are graphing rational functions, we're going to essentially fill out all the information we did in the first example, and then we're going to sketch them. Some of our examples are not going to have all the steps because it just takes up way too much space. But essentially what you're going to do is you're going to find the horizontal and vertical asymptotes and then sketch them. So for our first step here, I need a different color. I would factor the numerator and the denominator first. So the numerator factors to x plus 4, x minus 3. The denominator factors to x plus 2, x minus 2. Which notice that nothing cancels out. Remember to find your vertical asymptote. You're going to set the denominator factored pieces equal to 0. So we have x equals -2 and x equals +2. Okay, you have to look the x equals -2 and x equals 2 both times. Horizontal asymptote. If we look at the original problem, notice the degree of the numerator is squared, degree of denominator is squared. If the degrees match, you divide the leading coefficients. So in this case, y is going to equal 1. Now we're going to sketch those on the graph. This is what our graph now looks like. The next thing that we are going to do, according to our steps, is we're going to find the x and y intercepts. So remember, for x-intercept, we replace the y with a 0 and solve for x. When we do so, you're really only going to set the numerator equal to 0. So our factored numerator, x plus 4, x minus 3 equals 0, we will have x-intercepts at negative 4, 0 and 3, 0. Okay. For y-intercept, remember we're really only going to divide these constants because all of my x values are going to be 0. So my y-intercept is 0, 3. Okay, so now we're going to sketch those points on our graph. So we have negative 4, 0 and 3, 0. And remember, our y-intercept was 0, 3. Our third step is to do an xy table to get a few more points. We need to be able to make sure we have the appropriate shape for our sketch. So I would pick something to the right of x equals 3. I don't know, let's try 6. Okay, so when you plug 6 in, you can do it off to the side. 6 plus 4 times 6 minus 3 over 6 plus 2 times 6 minus 2, which equals 10 times 3 divided by 8 times 4. So this is 30 over 32. Okay, so 30 divided by 32 is a decimal, is about 0.9. Okay, and remember this is just a decimal approximation, so you can just do a decimal to the nearest tenth. Okay, so now we're going to approximate 6 and positive 0.9. For rational functions, your graphs are always going to approach the asymptotes, and sometimes, however, the graph will cross the horizontal asymptote. It's only for horizontal asymptotes that this occurs. They will never cross through the vertical asymptotes. Now, in our sketch, we need something in the middle. So I would probably try 1 and negative 1, and then go through the same process. When I substitute 1 in for x, you will get approximately 3.3. And remember, you can do this step in a calculator if you need to. For negative 1, you should get 4. So 1 in 3.3, somewhere about here. Oop. 3.3, 1, 2, 3, somewhere about here. And negative 1, 4. And remember, we're going to approach those asymptotes. Now, we need to do something to the left of negative 4. So, I don't know, let's try negative 8, maybe? Okay, so let's see. Negative 8 plus 4 times negative 8 minus 3 over negative 8 plus 2 is negative 6 times negative 8 minus 2 is negative 10. So it looks like we'll have negative 4 times negative 11 divided by 60, or 44 over 60. It's really, really close to 2/3. It is really 0.7-ish. So negative 8 and 0.7 somewhere about here. And remember, our end result graph is going to approach the asymptote. Ta-da! Try that you try.